Hi everyone, welcome again to Scientist Chats. This is week 8. As usual, a few of the guidelines. I'd like to ask all attendees under the age of 13 to please have a parent or guardian present during this session, as well as just like to remind everyone that this session is being recorded. So the final Let's Talk Science quiz is actually being held tomorrow, Thursday, June 4th. So I'm sure everyone is pretty excited for that one. Just have a few announcements for you all, just to let everyone know that we will be having 3 more weeks of Scientist Chats, despite this being the final week of the quiz. So, from June 10th, June 17th, and June 24th, we'll be having 3 more speakers. So, a little bit of exciting news for everyone here today. So this week, the quiz will be centered around engineering and technology. So, topics ranging from X-ray imaging to computed tomography, MRI scanning, ultrasounds, a lot of these techniques used in the medical field. So just take a look at the website. So what we'll be looking at is some of the science and machinery used to conduct these imaging techniques, just as well as some of the history behind X-rays and how we came up with these technologies that have changed human healthcare for the better. So this week we're joined by Dr. Marina Freire-Gormaly, who holds a PhD, and she's a professor in mechanical engineering at York University, as well as a former soapbox science speaker. Her research interests ranges, it varies massively. So I didn't list any here, but I'm sure she's going to go over a lot of that. A lot of very interesting machinery that she uses and develops to analyze a lot of problems that faces humanity, ranging from whether it be healthcare, solar panels, and much more. So I would like to please ask you and join me in welcoming Dr. Freire-Gormaly.
All right. Thanks for the introduction, Adisa. And just wanted to get started with my slide deck. So yeah, welcome everyone. Thanks for attending the lecture today. And so I'll be discussing about the design of smart and sustainable drinking water and renewable energy systems. And I'm really excited to share about my research and also to hear your different questions about engineering and technology. So to give a bit of a background, I'm working as an assistant prof in Lassonde Engineering at York University. So it's a really brand new school in terms of the engineering, and York is a very large campus in the north part of Toronto. It has a lot of liberal arts, and so it's really exciting to be able to do interdisciplinary research. I also previously did research at the University of Toronto. That's where I did my undergraduate, master's, PhD, and then a postdoctoral fellowship as well. I've also worked at Ontario Power Generation, and you might have heard of this company. They are providing all of the energy for a lot of the energy for Ontario using nuclear reactors as well as hydroelectric generating stations. I've also worked on some projects with the World Bank. So the World Bank helps to develop new policies and inform ways that we can support renewable energy. So this was on a report called Regulatory Indicators for Sustainable Energy. So in terms of the research fields, I've done some work on carbon capture and storage technology, and that involves a lot of the imaging that's in your quiz this week. I've also done a lot of work on solar-powered water treatment, which is the main focus of my research program. And we're starting to do some work on COVID-19 as well. How do the droplets spread, and how do we ensure that we can all stay safe when we go back to school and to work and to our offices? So I also wanted to give you a bit of a background on why did I choose engineering. So I think that it's really important that we all have a lot of different interests. We're not just scientists or interested in languages. There's all different parts of us. So in high school, I went to Mark Garneau Collegiate Institute. They have a TOPS program called Talented Offerings for Programs in the Sciences. And that was a really awesome time because we were able to do different outdoors activities like going to Algonquin Park, and also have a really great group of friends that I'm still in touch with today. And then I was also a lifeguard, so it's always fun to do swimming and be active. So I also really enjoyed playing music. So engineering and science is such a team sport. We can never develop new technologies on our own, and we really need to build on information that we've learned from others and also work in a team. So music really taught me that. And then in the top corner, there's some dragon boat racing, which I did while I was at Ontario Power Generation. So that was a really fun activity outdoors. In the center, this was while I was teaching an energy related course, and this is on the roof of a Toronto Hydro building in downtown Toronto, right on the lake shore. So you can see these panels in the background. They're a special type of solar panel that's a cylinder, so it means that the silicon cell can get light from the top and from the bottom. And that was a really neat technology that they have on the roof there. And for my undergraduate, I attended the engineering science program at the University of Toronto. And this one was also really hands-on. We did a lot of building of different devices and working in teams. So all of this really encouraged me to pursue a master's and then a PhD, and finally to start my own lab. So what do we do at our research lab? We're essentially designing smart and sustainable drinking water and renewable energy systems. And this involves doing different simulations, system models, optimization, and machine learning, and also looking at the experimental verification. So once you've developed something in the computer, you need to be able to test it in real life. And experimental work can help you do that. And this further informs our model development. And we also work with communities. So we want to be able to take what we've learned and developed and then put it into practice. Okay, so why is this important? Well, globally, there's 2.1 billion people worldwide that lack access to clean drinking water. And what's interesting is if we match it with where the places are the sunniest, so the places that have the highest solar irradiance are also in red, and we can match the places that need the water with the places that have a lot of sun. So this means that we can use solar energy to provide the power to clean the drinking water. So these small-scale solar-powered water treatment systems can help satisfy their water needs. So the main technology that we're using in these systems is called reverse osmosis. Quick video on what is reverse osmosis.
The core technology used at the Adelaide desalination plant is called reverse osmosis. First, let's explain what osmosis is. Osmosis is a naturally occurring process in which a liquid, such as water, spontaneously passes through a membrane. The membrane or semi-permeable barrier allows some molecules, like water, through, but other molecules, like the majority of salts, are unable to easily pass through the membrane structure. The flow of liquid through such a membrane occurs naturally to try and even out the salt concentrations between the two solutions. That is, the liquid flows from the less concentrated solution, such as fresh water, to a more concentrated solution, such as seawater. When the direction of liquid flow is reversed, it's called reverse osmosis. By pressurizing the concentrated solution, in this case seawater, we are able to force water molecules in the reverse direction, from the salty seawater side through the membrane to the freshwater side.
So So those reverse osmosis membranes are huge. They're the length of a room, and that's because they're providing the drinking water for the whole community, and that's similar to providing enough water for the city of Toronto. But the systems that we're building are a lot smaller. They can be put in a small shed, and I'll show you some of so one of the membranes, what it looks like, it's very short. It's only this long, so 1 foot long. It's only 1 foot long, and you can see that it's quite small. Okay, so reverse osmosis, the idea is that you just saw it in the video, but you have a low salinity water, so that would be drinkable, and then your high salinity water is on the other side. So by osmosis, you might have seen different egg experiments. The water will naturally go to the spot where it will naturally try to go from the low salinity to the high salinity to try to balance it out. But then in reverse osmosis, we need this applied pressure. And applied pressure means that we need to have a lot of energy, or a pump that is used in a pump to push the water in the opposite direction. So one of the main challenges with this research is that we need to run these systems without a lot of electricity, because we're only relying on solar energy. So during the evening, the system is off, and during the daytime, the tank is filling up, and during the evening, it's off again. So what this means is that on this reverse osmosis membrane, there's a lot of different foulants that can accumulate on the surface. So these different organic content that's in the water, or scales you might have seen in your shower, those little white specks that get stuck to your shower head. So all of that can build up on the reverse osmosis membrane and then decrease the amount of water that can permeate through. So this is what one of those systems looks like. We take in what are the water characteristics of that community, the solar insolation that's available, and the water demand. And then this is put into a system design, and the algorithm automatically chooses what pump should we use, what number of reverse osmosis membranes should we use, how big should the tank be. And do you notice anything missing here? So we've got solar panels, we have things to use the devices. So usually we would have batteries, but batteries are really expensive. So to take that out, to reduce the cost, we've taken that out, and then the system only operates during the daytime. So to test this out, we made this experimental water treatment system video to give you a virtual tour.
This is the reverse osmosis experimental equipment. The green tank allows for continuous agitation and temperature control of the experiment water with UV disinfection. The high pressure pump pressurizes the water to perform reverse osmosis in this pressure vessel. This automated control valve allows for maintenance of the recovery ratio throughout the experiments, and the flow rates and conductivity are continuously monitored. A set of control electronics and an NI instruments device allows for automatic control and continuous data collection throughout the experiments. This is the LabVIEW interface shown on the computer as well.
That's a pretty quick tour, but what we get out of that data collection is different graphs like this. So we can take the amount of water that's produced and then measure it continuously, as well as the amount of salts in that water, and we get something called the normalized permeability of that membrane. So if it gets worse, that means that the membrane has become clogged with all these different foulants or scales, and I've taken out the time when the system is shut down. So one of the big research questions that scientists were wondering is, if we run these systems intermittently, then we won't be able to measure very well. We won't be able to produce enough water for the communities. So instead, I was able to show that even though we're operating it intermittently, we're able to have a reasonable membrane permeability even after the 8 days of operation. We also wanted to explore a little bit about the biologic activity. So we measured the ATP. So this is a surrogate number for seeing how much DNA is left on the membrane surface. It doesn't tell us whether the cells are alive or not. So it's a very bulk number, and this requires more investigation. But we saw that the intermittent operation had more accumulation of this biologic activity. So it's really important that we rinse the membrane prior to shutdown. So in this set of tests, we're just using antiscalant, but we're not doing any rinsing. So here, we're doing a rinse. After we shut down the system, we flush the whole system with really clean water, and that helps remove a lot of the organic content and different scales that are on the surface. So you'll see that after the 8 days of operation, we're able to have a much higher membrane permeability than when we're not rinsing. And also, the biologic activity was a much lower when we were operating it with this rinse prior to shutdown. Okay, so we also came up with this fouling mechanism from intermittent operation. So the idea is that we notice this spike at the beginning of each day. So you can see on this previous slide, oops, there's a big increase in the membrane permeability at the beginning of each day. So we're getting a lot more water flow at the beginning of the day. So the reason is most likely because we have this flow reversal. As soon as the system is shut down, now that membrane can operate using osmosis. So the permeate water will go into the feed water side. That helps loosen all of these balanced scales and provides a bit of a natural rinse of the membrane very close to the surface. And then at the beginning, we get a lot of air inside of the lines, and so we get a turbulent startup, which helps wash away these loosened balance and scales. Okay, so we took all of this information and we put it in a simulation-based design optimization. It was essentially a computer program. It takes all the different variables, how much solar insolation, how much water, and then it runs the system. It pretends that we know all of the information about the next 5 years, 10 years, 15 years, and then it figures out what is the best design. Should we pick this pump or that pump? Do we need 8 membranes or do we need only 1? How big a tank do we need? And then it comes up with the system design. So it'll tell you buy this reverse osmosis membrane, buy this reverse osmosis pressure vessel, buy this number of solar panels. There is some small battery storage just to run that rinse, but it's not enough to run the system overnight and continuously. So overall, we were able to show that lower reliability systems were not significantly cheaper. So we definitely want to be able to provide water every day of the week for the community. And also, depending on, we originally thought that if we have a system that's being designed, say in Ghana, and a system that's being designed in Mexico, it'll be a completely different design. But what we found was that there were some sizes of the system that you could have almost the exact same pressure vessel and water tank and number of membranes. So that means that we can do some mass production of several system configurations for lots of different places, and that'll mean that we can help meet the needs of these communities more quickly, because you'll have the advantage of advanced manufacturing. Okay. Oh no.
The 3D prototype is built layer by layer by the green laser. Videos of rapid prototyping. So you saw there were a lot of different pieces in that system, and one way is to use these 3D printers. So I just thought I'd bring you inside the lab to see how does the 3D printer work. This is a special type that uses a resin bath, and I'll let you see the video. The 3D prototype is built layer by layer by the green laser, following a different path for each individual layer. as it cures the resin to build up the 3D prototype.
And then for laser manufacturing, it also uses a laser beam, but this laser beam is concentrated so that it can cut through acrylic. So I'll just show you this cutting through the acrylic. And when you see the bright flashes, it's because it's hitting the metal underneath. The beam is so strong that it's hitting underneath of the acrylic. So these are some of the tools that we use when we're developing different components in the lab. So I thought I'd give you some more information about geologic media characterization, which is some of the different tools that you've been looking at, the different imaging tools that you've been looking at inside of your quiz prep. So this involved taking X-rays of a rock piece, and we use microcomputer tomography, and that lets us see at a very tiny scale. So this is the resulting image, and then we can combine all of these individual slices of the image into a 3D space. And then we use something called a pore network model to find out all of the empty spaces in the rocks, to find out how well connected they are. And this is used for carbon capture and storage. It can also be applied for mining, pumped air storage, or even looking at natural gas reservoir modeling. So one of the disadvantages of this technology is that you can get really, really high resolutions, but rocks still have even more layers of granularity if we look at a scanning electron microscopy. So here we're looking at, this scale is 20 micrometers versus 1,000 micrometers. So if we zoom in on a tiny spot, we can see there are even more tiny pores as we dig in deeper. So I was looking at different thresholding mechanisms to try to quantify the porosity that isn't captured by our microcomputed tomography. Some of the new projects, we're working with the Asian University for Women in Chittagong, Bangladesh, and Chemists Without Borders to see what are the arsenic levels in the groundwater. And we're also doing some experimental investigations of robust energy water systems. So this is in collaboration with Gambia Next Stratos Inc. And also it was supported by IDEA's pop-up city competition from the Department of National Defense in Canada. So we have lab scale experimental verification. We're also doing computational modeling. And the goal is to collaborate with Northern Canadian communities for a pilot scale system that's powered by renewable energy. So this video, some of our newest work, which we're starting up at York University, looking at how do COVID-19 droplets transfer within a room, and how can we take that into consideration when we're doing the heating, ventilation, and air conditioning of buildings. So this video isn't by my lab, but it's just gives you a sense of what are some of the challenges. So you can see when someone talks or speaks, they have little droplets, and some of them will continue to flow around the room even after they finish speaking. The larger particles will drop to the floor. You can see they hit the guy's shoe and their clothes, but some of the very light droplets, they remain suspended in the air, and they can go into your building and travel around for even 20 minutes or an hour. So this is part of the reason why we're all staying home these days. but there's ways that we can improve our HVAC, our heating, ventilation, and air conditioning to try to remediate these micro droplets and to prevent the spread of COVID-19. So everything happens in a team, and our lab is growing, but we have a few summer students and a master's student working on these projects, and it's a really exciting time to be doing research and also trying to come up with new solutions to sustainable water treatment. So thanks.
Perfect. Thank you so much for that presentation. It's always fascinating to see the application of these technologies into the real world studies. Thank you for that. You spoke a bit about the modeling for in terms of dealing with the COVID-19. Could you expand a bit more on how engineering techniques and technology could be used to fight against COVID-19?
Sure. So a lot of the engineers that are working on this right now are looking at these droplets. So they'll do different simulations, and you can use different software to see how do these droplets move around in a room. Are there ways that you can use ultraviolet? So you saw in the experimental water tank, there was a UV light. Just UV is really good at killing bacteria or viruses. So if you have it at a high enough strength, then inside your heating and ventilation and air conditioning. So in hospitals, they already use this, where you'll have some UV light, and then you can purify and sterilize the air before it goes back into the room. And also, engineers are doing a lot of work on and scientists definitely are doing a lot of work on the testing of COVID-19. So taking swabs, you've heard a lot about how people are using the nasal swab, but they're trying to see new tests, like can you take a little bit of saliva so it's less invasive. One of the challenges is when you take a swab that's going all the way up your nose, and the person feels really uncomfortable, and they're more likely to cough, which if they're infected will be even worse. So it's really important that we look at different ways of testing and seeing if there's safer ways that we can ensure that the population doesn't have COVID-19 and also isn't spreading it to the workers who are testing them.
Okay.
Yeah, and then a third way is obviously on the viruses. So like, how do we make a vaccine for this virus, and what does it even do, and how does it work inside the human body? And some people are doing some really exciting machine learning techniques, trying to like take all of the information that's already been done and being able to really learn about what's happening and how can we improve the situation and create a new vaccine quickly.
Okay, very, very interesting. So I have a question here about how expensive are these remote osmosis systems?
Yeah, so once you put the whole system together, it depends on how much water you're producing, but it's around $1 per meter cube. So that's like $1 per 1,000 liters of water that's produced. And if you're buying it off the shelf, then it's like $5,000 for, say, 1 meter cubed, or $10,000 for 10 meters cubed. So it depends on how much water you're producing. But it's on par with what the municipal, like it's a little bit more expensive than municipal water, but it's much cheaper than the alternative, which is using a truck and then transporting it all the way across the country. And by the time it gets to that community, it might have already grown a whole bunch of bacteria in that tank. So
yeah. And would you say that using some of the 3D printing technologies, would that help to cut the cost as well of putting the system together?
And also by having different systems that we can put together quickly, like those control electronics you saw. So some of everyone watching, you might have used different Arduino tools or different small electronic circuits that you can build on your own. So there's ways that we can use rapid prototyping to develop things more quickly. Oh, and on the COVID-19, definitely advanced manufacturing is really useful for the production of personal protective equipment. You might have seen those masks and the hangers that are made on the 3D printer.
Okay.
Yeah.
Very, very helpful technology. So I have another question here of how long did it take you to model and design your reverse osmosis system?
So it takes, so building the model in itself took probably about a year to really make it a really robust computational model that we know that it's doing what it's supposed to be doing and that it's considering all these different components. But once you are putting in all of the information, then the system can determine the optimal design within about an hour on a desktop computer. So it has to go through all these millions of combinations and then testing every hour at a time. So it takes a bit of computational time.
Okay. And what are these the reverse osmosis membranes made out of?
So they're a polyamide composite material. So I have a piece here that I can show you. So it has like a shiny side. I don't know, it's hard to see. So there's a shiny side and then there's a less shiny side. And it's made out of a plastic polymer on the top. That's called the active layer. And then on the back, it uses fiberglass because it has to be very strong. These systems operate at 300 PSI, so that's 10 times more pressure than what's inside of your car tires. And that's on the low end. The higher end, they might operate even 1,000 PSI. So these membranes, they have many different layers. So this is they call it spiral wound element, and it has these turbulence layers, which is like a mesh. You can see it's like a screen, and then it has the shiny membrane that's actually separating it, and then on the other side, it's called a permeate collection mesh. So this mesh is even finer. You can see that you can see through it, but it's not as clear as the other one. So that helps guide the water through the spiral into the permeate collection tube.
Okay. Very interesting. So I have a question here that steps away from what you were speaking about. It's about how do airplane wings generate lift?
Oh, okay. So this is more on the aerodynamics. But you essentially have a wing, and then depending on the shape of the wing, so usually it's like an airfoil, right? So it'll make a pressure. There'll be a spot of very low pressure, and then that helps generate the lift. So there's different ways to determine whether an airfoil will produce the right lift. So you have different measures like chord and these things. So you're essentially creating a vacuum at some point, and then it helps generate lift. It'll take, that's a very good question. I think a bit longer to explain that one.
You could elaborate a bit more if you would like.
No, it's okay.
No? All right, so I have a question here about, this one again is away from directly in your field. It's just talking about development of vaccines. Okay, so I know you mentioned using some of your engineering technologies to increase the rate at which the vaccines develop, but you mentioned more high-speed technology. Could you elaborate a little bit on that?
Oh yeah, so I just read it recently, but I think what they're doing is they have an algorithm that'll use natural language processing. So it's a type of machine learning. And then it's automatically reading all of the articles and research papers that are available online. And then by using words that the researcher types in, it'll let them pick out the most relevant and most useful articles that are related to it. And on the vaccine side, like, they're looking at different proteins and different structures. And so if you have all of this database of information, trying to pick the right design for your vaccine is very challenging. So they're trying to use different computational methods to pick out what is the best way to do it.
All right, so I now have a question here about bridges. So the question asks, how can bridges stay up in water?
Oh yeah, so the way that they stay up in water is that you have the design of your bridge has essentially these piers. So if you think of the Prince Edward Island Bridge, it's one of the biggest, longest bridges in the world earlier, but now it's been beat by another bridge. But they have all these piers inside the water. So your water, you can see it from the side, but then the ground is underneath it. So essentially, you need to provide a pier that can transfer the weight of the bridge to the ground. And that's how it's standing up in the water.
And so I have another question here about your system. I know you mentioned it, like, so I think you might have answered it, but the person who asked again, so see if I could recall, you mentioned it taking about a year to put together all the designs and running the models that you require to put together that reverse osmosis system, correct?
Yeah.
Okay, perfect.
So it takes time to make the algorithm, but then once you have the algorithm, then you can just run the whole simulation in an hour, and the user will be able to choose what is the best design quickly.
Okay, perfect. So I have a question here about why does high velocity result in low pressure?
Oh, okay. So this is on the airfoil.
Yes.
So if you have a really high velocity, when it's going over when you have the shape of your airfoil, then you end up creating different pockets under that wing. So it's quite counterintuitive, but you always need to balance this Bernoulli's equation. So it has all the different factors in it, and when you end up having a high velocity in one spot, then it means your pressure has to compensate in another spot.
Thank you for that. I learned something here today as well. Thank you for that. So I have a question about your research requires you being, I know you do a lot of modeling and all that, but your research requires you being in the lab physically at times. How have you and your team dealt with this COVID lockdown in terms of ensuring that your research continues?
Oh yeah, so it's pretty challenging not being able to just drop in the lab and then build some things. But we've decided to focus more on the modeling. So we found that it's been useful to work on a new project, the COVID-19, doing modeling in different, so we're using ANSYS. We can also use different modeling software. And then on the renewable powered water treatment side, we can always do work inside the lab, but sometimes it's also useful to step back and then redesign your computational algorithm. You can also do, we're doing a lot of literature review, so making sure that we're thinking of brand new projects and staying on top of what's happening in the world so that we can be the most useful when we're back in the lab later.
Always staying active, always reading, always practicing, always writing. I'm sure some of your students and probably yourself are writing journal articles.
Yeah, exactly.
Right.
So one of the main, I'd say there's three main components to research. You've got to write the proposals to get the funding, and then you need to do the research in the lab or on the computer, and then you need to communicate your results. So that's your journal articles.
Okay, perfect.
Yeah.
All right. So I have a question here from I know we discussed in a previous week about where we had an epidemiologist on, but I don't know if you could help answer this question. So the person is asking about the nature of vaccines in terms of, yeah, so like if they test a vaccine and it doesn't work, how does it affect the person they tested it on? Can you provide shed some light on that if possible?
Sure. So my understanding of the vaccines is that they'll test it as quickly as they can on animals and then go to human trials after they've ensured that it doesn't cause any negative effects. And also, usually with these really dangerous types of viruses, they won't put a vaccine that has live virus inside. So they'll put a dead virus and then they'll give that to the person. So if the vaccine doesn't work, then they'll be monitored a lot. Like they'll make sure that they're not getting sick with COVID-19, and they'll be monitored very closely. So as soon as they start having any symptoms whatsoever, they'll be giving them all of the medical attention to make sure that they can recover.
Perfect. And as we have previously discussed with the one of our past chats, these vaccines usually take a lot of time to be produced. So a lot of testing is going to take place before it's tested on a human being. So the chances, a lot of work is done prior to human testing. That's the best I can leave it at.
Yeah,
so,
and I guess also they try to take the healthiest people to test it on.
Yeah.
Not the most at risk.
Yeah, perfect. So I think we'll wrap up pretty soon. But I actually have a question.
Sure.
So in terms of after you've developed, because you mentioned using some of the solar powered water filtration system in regions that may not have access to other technologies at the time. So is it that when you develop this technology and you test it, would you be giving them the ability to manufacture it in and of themselves and sharing that knowledge with them? Or is it that you'll be trying to distribute the actual devices for them to apply at that point?
So it's a bit of a combination of both. We want to be able to train the communities on how to operate the system. So we have an operating system that was part of my earlier research in Mexico, and the community fully owns it and operates it. Like, we don't even really interact with them much. They have support for figuring out how to buy the replacement membranes and fix the system when they need it, but they're fully in control of the system. So it's really important that the community members are fully trained, and also they know how to fix it, because the worst thing you can do is like give a technology and then it breaks and just sitting there doing nothing. So then on the other side of it, we also, some of the future goals are really to how do we mass manufacture these and get them into the communities that need them, and looking at the other aspects of like how do we engage the community in the design in the first place so that they feel a huge ownership on it. So that's why we wanted to have these computational design tools to be able to let them be in control of the process too.
Okay. See if there aren't any more questions, I think we'll wrap up pretty soon. So
I can show you a bit of a video
definitely
on how a wing works, I guess.
Sure.
So it's a pretty short video. 1 second. Gotta share screen.
To Minute Physics Studio to.
Oops.
Ensure this.
There we go.
Perfect.
Explain how a wing actually works. Hang on. Something doesn't feel right. That's better. Now, everyone knows that a wing generates lift due to its characteristic shape. Since air travels farther over the top of the wing, it must go faster than the air underneath so that both streams meet up simultaneously at the trailing edge. And according to Bernoulli's principle, faster flowing air exerts less pressure than the slower air beneath the wing. This pressure difference creates an upward force, lift. Job done, right? Nope. This simple explanation, taught in many textbooks and classrooms, has obvious problems, like how could a plane fly upside down? Some planes, like the Wright brothers, had nearly flat wings, so presumably air would travel the same speed over both sides and there would be no lift. Plus, experiments show that air streams don't meet up at the back of the wing. Air over the top goes significantly faster, reaching the trailing edge first. So how does a wing actually generate lift? Well, the key is the wing must deflect air downwards. This can be achieved using asymmetric or cambered airfoils, or by increasing the angle of attack. Air under the wing is deflected down, and by the Coanda effect, air above the wing is guided along its surface and down as well. Since the air is slowed and deflected down by the wing, it pushes the wing up and back, lift and drag. This is in accordance with Newton's third law of motion. But hang on, if you can explain lift only using the deflection of air and Newton's laws, then the Bernoulli explanation must be completely wrong. Well, no. Air over the top of the wing does go faster than air beneath, creating a pressure difference that generates lift. Then this Newtonian explanation is unnecessary rubbish, and the original explanation was right. But that's not true either. The original explanation incorrectly assumed that air over and under the wing must reconnect at the trailing edge, and there was no mention of deflecting air down. Each explanation done correctly completely accounts for the lift generated by a wing. They're just two different ways of looking at the same thing. So next time someone brings up the standard misconception, you can tell them that explanation just doesn't fly. And if you like that, you've got to check out Minute Physics.
Would you mind sharing that link in the chat, please?
Oh yeah, sure.
Perfect.
Well, in science, there's always many ways to explain things.
That is definitely true. And so I know you're sharing the link right now.
Oh
and,
yeah, sure. Okay.
Perfect. So with that, do you have any closing words, any final words for our viewers today?
Oh, I think it's really good to stay engaged with science and different fun activities during this time. I realize that everyone's at home, but I'm really glad that you're all participating, and I hope you have fun doing the quiz and also learning about science from home. I encourage you to get outside, do some gardening maybe, or do different activities. So if you have any questions, you can always reach out to.
All right. Perfect. All right. Thank you very much for attending, everyone. And I would like to thank Dr. Freire-Gormaly for joining us today and taking the time to explain her work and some of the questions that you have. So with that, thank you.
You're welcome. Thanks a lot for having me.
All right.